So this lecture will give you information on the LDH experiment, some of the experimental basics that you're going to be using to do, and some of the theory behind why you're finding Vmax and why you're finding Km and how we're able to use them. So in this experiment, in the cuvette, you're going to place your 1 ml of your MOPS, and you're going to place your 10 microliters of pyruvate, and then you're going to zero the cuvette with only the MOPS and the pyruvate in that cuvette. Then after you have zeroed it, then you can add the NADH. Once you add the NADH, you're going to have a large positive number, 1.5, 1.8, 2.1, something like that, a large positive number in your spectrophotometer, and this is due to the reading, the absorbance of the NADH. As soon as you have that number, that's your time zero reading, and then you're going to add your LDH. Now make sure that you've mixed after you add the NADH, because otherwise you're going to get very unsteady readings if you have unequal concentrations through the tube that are maybe floating in little currents. So you're going to mix after you add the NADH, you're going to add the LDH, and you're going to mix again. But to mix, I like to get a little piece of parafilm and invert it. It's much better than trying to pipette up and down. If you add 3 microliters to 1 ml and then try to pipette up and down, it's going to take a long time to get that 3 microliters mixed in that 1 ml. But if you have a piece of parafilm on the top and you're just inverting a couple times, it goes pretty quickly. Now your first reading needs to be within 30 seconds, and you need time for the spectrophotometer to be able to give you that first reading. It's not instantaneous. It sort of thinks about it for a minute. So you want to get it in well under that 30-second timeline. So adding the LDH, mixing, putting in the spec, waiting to get basically a steady but steadily decreasing number, because once you add the LDH, you're going to see your number decrease, decrease, decrease. And you're going to read it at 30-second intervals. Remember to keep the enzyme cold. You don't have to keep the other items cold, but you do have to keep only the enzyme cold. So what you should see, you're going to start out at a fairly high number. You're going to start out at around 1.8 maybe, and have a very high number to begin with, and the number is going to be going down, 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 down. And so this is your dA/dt. This is your change in absorbance with change in time. And at a certain point, it's going to level off. It's going to stop changing so quickly. So when you graph it, after it starts to level off, you cannot use those numbers. You can only use the numbers that are your initial dA/dt. After you have approximately 10% of the substrate converted to product, you're going to start seeing a slowing of the reaction, because the back reaction starts occurring. So only your initial linear dA/dt, and you're going to get all those points. So you're going to graph all those points, and then you're going to select just the first linear ones to get your dA/dt. Then you're going to convert your dA/dt to velocity by using the extinction coefficient for NADH. And the extinction coefficient for NADH is 6.2. So 6.2 changes in absorbance per millimolar. And so let's say you do your absorbance, you've calculated out your dA/dt, and you find your absorbance drops at 0.0093 per second. Or if you do it in minutes, 60 seconds per minute to get it in terms of change in absorbance per minute. Either way is fine. And then you're going to divide by the extinction coefficient, because remember Beer's law, absorbance equals the extinction coefficient times the path length times the concentration. And we're trying to find that change in concentration, that rate of reaction. So the absorbance right here divided by the extinction coefficient divided by the path length also, but remember that's 1 centimeter, so we're not actually including that because it's just 1. And so you're getting your you're getting your velocity right here, your rate in terms of velocity of 0.09 millimolar per minute. If you need it in micromolar, that's 90 micromolar of pyruvate per minute. So So when you're doing part A of the reaction, this is what you're going to be starting with. Then you're going to go to part B of the reaction. And in part B of the reaction, you're going to be varying the amount of your enzyme. So you're going to be doing the same thing. You're going to be starting at a very high number, and you're going to start with 3 microliters of enzyme, and you're going to get the D80T for that. Now, here's a little secret. If you do part B on the same day that you do part A, with the same enzyme mix, in other words, the enzyme has not had to be remade or anything like that, so there's a slight change in concentration for any reason. So if you do part A and B on the same day, you already have 3 microliters done. So then you can just do 4 microliters or 5 microliters or 6 microliters so that you can have 4 points on your next graph. So you've already done 3, and then you'll do 4, 5, and 6 microliters for part B. So the rate is going to change as more enzyme is added. So you're going to get a steeper and steeper rate as you keep adding more enzyme. It's going to be faster and faster. And then you're going to be graphing, you're going to be plotting velocity versus the amount in microliters of enzymes. So what you're going to get is for 3 microliters a certain velocity, for 4, for 5, for 6 it may still be linear, or it may start curving and leveling off. And so when it levels off, that says, okay, at this point my enzyme has now become limiting. So you want to make sure you're using significantly less enzyme than the area where it becomes limiting. So this is an example of what people are doing when they're trying to calibrate how much enzyme they should be using in the reaction. So then you're going to go to the next section, and in the next section you're going to be exploring the effect of pH on velocity. And you're going to be doing this exact same reaction that you did in part A with 3 microliters of enzyme, but now you're going to be doing it at different pHs. You're going to be doing it at pH 7.5 and pH 8 and pH 8.5, etc. So you're changing the pH, and as you change the pH, the velocity will be either greater or lesser than your initial comparison point. So you can graph this right here. So you have a graph of velocity versus pH. So you're finding where your maximal activity is. That's the best pH that you want to use. So if you were doing this for research, for example, you would say, okay, experimentally, I want to be conducting myself I want to be conducting all my experiments near the pH maximum. In part D, you're going to be exploring the effect of changing the substrate concentration on velocity. So as you have greater or lesser amounts of substrate, you will have greater or lesser velocities. As you go towards infinite substrate, you're going to be approaching Vmax, but you're never actually going to get to Vmax. You just approach Vmax. So this graph doesn't actually tell you much because you don't really know where Vmax is. So what you do is you use Lineweaver-Burke equation, and the Lineweaver-Burke equation tells you to graph 1 over V versus 1 over S. And when you put those same numbers of changing velocity with changing substrate concentration into a Lineweaver-Burke graph of 1 over V versus 1 over S, here you are approaching your maximal velocity right here, Vmax, where it hits the intercept. Where it hits the other intercept, this is minus 1 over your Km. So you would experimentally be able to determine what is your Vmax and what is your Km for this particular enzyme. The next thing you're going to be doing in the experiment is finding the type of inhibition. So you would use, in this case, we're going to use Cibacron blue as an inhibitor. And so you would add Cibacron blue as an extra into the solution before you add the LDH. And you would say, well, how does this change my parameters? How does this change my Vmax? How does this change my Km? So you'll remember from the lecture, If it's non-competitive inhibition, as an example, as you increase the amount of inhibitor, you are changing your Vmax. Your Vmax becomes less. But you are not changing your Km if it is non-competitive inhibition. So as you do 1 over V versus 1 over S with no inhibitor, and then 1 over V versus 1 over S with some inhibitor, and then you're actually going to be doing this with 2 different concentrations of inhibitor. So you're going to be increasing and then increasing again. So you should have 3 lines all on the same graph so that you can do a comparison. So when you do that, you'd say, okay, here, here, and here, but all coming to the same Km. This says non-competitive inhibition. On the other hand, if it looked more like this, you'd say it's competitive inhibition, where you have the same Vmax but differing Kms. So this is what a competitive inhibitor plot would look like. An uncompetitive inhibitor, you're changing both the Vmax and the Km. You're getting approximately parallel lines in an uncompetitive inhibitor. And if you have a mixed type inhibitor, remember from the lecture, your point is going to be somewhere in here. It's an offshoot of non-competitive. So if it was truly non-competitive, you'd have the same Km. But in this case, you have Vmax changing and Km changing with a crossing point right there if it is a mixed type inhibitor. Now, one of the questions you will be asked to answer at the end of your lab report asks you, if you have your experimentally determined Vmax, you want to find the activity of your lactate dehydrogenase in units per mil. This is when you buy a bottle of enzyme, this is how it normally arrives. It will tell you how many units per mil are in that bottle. So the definition of a unit is 1 micromole of substrate going to product in 1 minute. So if you take your Vmax, so our Vmax, we just figured out a minute ago, our velocity, we'll say it's Vmax in this case, was 90 micromolar per minute. So 90 micromolar per minute is 90 micromoles per liter per minute. But you have to account for 2 things. You have to account for how much enzyme did I add to get that Vmax, because remember that your Vmax is related to the amount of enzyme that you had as well as to your catalytic rate. So with greater amount of enzyme, you're going to have a potentially greater Vmax. So you need to account for how much enzyme you added to get that Vmax. So in this case, we had 3 microliters, but we want to be able to say, we want to be able to give it in mils because we're going for units per mil, not units per microliter. So we need to put our volume of LDH in terms of milliliters, so 0.003 milliliters was 3 microliters. And we also need to account for the volume in the cuvette. So that entire volume of the cuvette was 1 mil, but we're not canceling mils, we're canceling liters. So we need to put it in terms of liters. So 0.001 liter in the cuvette, so we can cancel liters, and we're putting it in terms of units of mils. So when we do that, the units come out to be 30 micromoles per minute per mil. So 30 micromoles per minute per mil. And we remember we defined up here that 1 unit is 1 micromolar per minute. So 1 unit is 1 micromole per minute. So that's a unit right there. So 30 micromoles per minute per mil is 30 units per mil. So this is what you're going to do with your Vmax to be able to find how many units per mil you had in your solution. And then, like, one of the test questions I like is, well, if you had this dilution, because remember you've already learned about dilution factors in previous labs, if you had this dilution, what was the concentration maybe in the original container? So be prepared for questions like that, which build on knowledge, basic chemistry knowledge that you should have. Okay, so let's talk about why getting these parameters are so important. To remind you, the Michaelis-Menten equation, V is Vmax times S over Km plus S. That's an equation you need to know, the Michaelis-Menten equation. But we've also talked about things like Lineweaver-Burke equation. So where does that Lineweaver-Burke equation come from? Well, it basically comes from doing algebra on the Michaelis-Menten equation. So if you do, and you don't have to know how to do this algebra, because frankly I had to look it up myself of how to do the algebra. So if you then divide both sides by Vmax, and then you invert, so you're getting V over Vmax is S over Km plus S. You invert, so now it's Vmax over V is Km plus S over S. You cross multiply those terms, so now you get Vmax times S equals V times Km plus V times S. And remember, I'm not expecting you to be able to do it, I'm just trying to explain to you all the algebra that was done to be able to convert from one equation to the other. And so divide both sides by V, so you get Vmax S divided by V is Km plus S. Then you divide both sides by Vmax times S and then by V, and you get an equation that looks like this. 1 over V is Km over Vmax times S plus S over Vmax times S. You cancel out the S's on that last term, and you get to 1 over V equals Km over Vmax times 1 over S plus 1 over Vmax. This is the Lineweaver-Burke equation. And it's an equation because it's in the form of a line. Y equals mx plus b. So this is why you are graphing 1 over V versus 1 over S in the Lineweaver-Burke equation. The slope is Km over Vmax, and the intercept is 1 over Vmax. So this is how you're going to do the graphing to find some of those parameters. Let me switch gears for a moment to talk about some of those parameters. One of the parameters that you're finding is the Vmax. And the Vmax is the limiting maximal velocity that is observed when all enzyme is present as enzyme substrate complex. So basically, you're saying the Vmax is your catalytic rate times the amount of enzyme. So the greater the amount of enzyme, the greater the amount of enzyme substrate complex you're going to have. So when all of your enzyme is in an enzyme substrate complex, you're maximizing out your potential velocity because it's being multiplied by that catalytic rate. So the other thing that you're going to be finding is you're going to be finding Km. And Km is a constant that's going to relate the velocity of an enzyme-catalyzed reaction to the substrate concentration. And this is because intracellularly, if the substrate concentration intracellularly is much, much less than the Km, this means that your velocity becomes very sensitive to changes in substrate concentration, but most of your catalytic potential is wasted because your velocity is much, much lower than your Vmax level. On the other hand, if your intracellular substrate concentration is much, much higher than your Km, it doesn't make any physiological sense because the velocity cannot exceed Vmax. The difference between the velocity at a substrate concentration equal to the Km and a substrate concentration 1,000 times the Km actually is only twofold. So you're wasting all that energy. So remember, you have to think about evolution. And evolutionarily, our systems are going to try to make the most of what they have. If your intracellular concentration of your substrate is higher than it needs to be, your body's wasting a lot of energy making that substrate when you're not really using it effectively in your cells. So you're basically, you're not like the best that you can be type of thing. And likewise, if it's much less than the Km, you're wasting a lot of your catalytic potential. So evolutionarily, we've adapted so that the intracellular concentration is basically approximately your Km. So Km is a constant for a given enzyme, and it's used to compare enzymes from different tissues or organisms. So if one group gets a KM from mouse and another group is working on an enzyme of rat and gets a KM, from rat, they're somewhat close, but they want to know if they're working on the same enzyme. So they're going to use their KM, and if the KM is about the same, they're going to say, okay, well, we're probably working on the same enzyme. If the KM is wildly different, then they're going to be able to say, okay, well, this is actually the different protein. Maybe it catalyzes the same reaction, but it's actually evolutionarily a different protein. Now, we've talked about K-cats and we've talked about KMs, but K-cat divided by KM is the rate constant for the interaction of this substrate and the enzyme, and it's called the specificity constant. And it basically measures catalytic efficiency because it's taking into account both the rate of catalysis for a particular substrate and the nature of the enzyme-substrate interaction. And remember, we've said that is the Km, that dissociation constant. So this K-cat over Km is used to compare enzymes' preference for different substrates. So an example of this that you may remember from your basic biochemistry is chymotrypsin. And if you remember chymotrypsin, chymotrypsin tends to cleave next to bulky hydrophobic side chains. So it will cleave next to tryptophan, tyrosine, phenylalanine. All of these fit into the binding cavity of chymotrypsin. It will not cut next to glycine at all. So the shape of that enzymatic interaction, the Km is very different if it's trying to cut next to glycine than if it's trying to cut next to any of those bulky hydrophobic side chains. So this Km over this K-cat over Km number is basically a specificity constant. Now, we've talked about Lineweaver-Burke and 1 over V versus 1 over S being what you're going to graph for the experiment. But you need to know that 1 over V versus 1 over S is not the only thing that is used in enzymology. Another example, and there are many different equations that are used depending on what people are interested in. One of the other equations that are used is the Edey equation. Now, one reason that somebody might not want to use Lineweaver-Burke, if they're very interested in finding an accurate Km for their enzyme, well, the least accurate part in a 1 over V versus 1 over S plot is where the substrate concentration is the lowest. And the substrate concentration is the lowest in these points right here, because this is 1 over S, remember. So these are the most inaccurate numbers right there for substrate concentration, but they have the greatest effect on the angle, basically, of the line, of the equation of the line. So if these are off a little bit, it can put your line maybe this way or maybe that way. It might not affect the Vmax very much, so if you're interested in Vmax, hey, Lineweaver-Burke's a great way to go. But if you're interested in the Km, well, a little bit of inaccuracy out here can really skew your Km and give you, because it's extrapolated here, gives you a very inaccurate Km. So someone who's more interested in the Km uses something like the Edey equation. And the Edey equation, V over S equals minus 1 over the Km times V plus Vmax over the Km. Equation of a line, y equals mx plus b. And the graph's going to look like this. So you're graphing V over S versus V, and your slope is minus 1 over the Km. So in this case, all the points equally are contributing to the slope of the line, are contributing to your Km. And so you've graphed V over S versus V, and where it meets right here, that's your Vmax. Now you can investigate inhibition in this also. And the parameters are the same. So remember that if you have a competitive inhibitor, Vmax is the same and Km changes. So if you have a competitive inhibitor and you graph it in an ED plot, Vmax is the same, but the Km, which is the slope, remember, the Km is going to change. If you have a non-competitive inhibitor, so remember a non-competitive inhibitor, if you did a Lineweaver-Burke plot, you learned that in a non-competitive inhibitor, the Vmax is changing and the Km is staying the same. So here you have in a non-competitive inhibitor, the Km staying the same, so the slope staying the same, but the Vmax right here is changing. On the other hand, if you had a uncompetitive inhibitor, your Vmax is changing and your Km is changing. Now, I would not expect you to realize that this one is going to go, say, this way necessarily. Well, with greater inhibitor, going this way, unless you were like trying it out and graphing it for yourself. But I have been known on exams to give problems that ask you to remember these particular, what's changing, what's not changing, and here's an equation you've never seen before, so tell me what type of inhibition this is based on the parameters that you are seeing. So make sure you have a basic understanding of all of this.